All right, what's up, guys? So here is another application of using a pKa table. Okay, so we can use pKa to compare a basicity of bases. If you go back to GenChem 2, you compare a basicity by looking up the pKb value of each basis, right? But that's going to be like too complicated, and some of those are not even available. But we have pKa. We know pKa. Use pKa is much better. Okay. And we already have it anyway. All right, so how do we use it? I'm going to show you how to. All right. Let's say if I ask you, all right, we got chloride ion and hydroxide ion, who's more basic? Now, you don't have to look up pKb. Use pKa value, and here's how we do it. All right, first of all, you will draw a conjugate acids of these two, and you compare the pKa of them, who's more acidic. Okay, so the conjugate acid of a chloride ion, of course, that's hydrochloric acid, and for the hydroxide ion, that's water, right? And the pKa, you know, hydrochloric acid is more acidic. You know that. Now, a stronger conjugate acid has a weaker conjugate base. Okay, a stronger conjugate acid have a weaker base. So who's stronger? Of course, hydrochloric acid is much stronger acid than water, which means that its conjugate base is a weaker base. Okay, it's a weaker base. It's opposite. Strong acid has a weak conjugate base. Weak acid have a strong conjugate base. So hydroxide ion is a much stronger base than the chloride ion. Okay, so strong conjugate acid, weaker base. It go opposite like that. Let's try one more time. Okay, I have an ethoxide ion and amide ion. Who's a stronger base? Well, you're gonna draw it out the conjugate acid of these two to be an alcohol and an amine. Okay, we have an alcohol and an amine. All right, compare pKa. Who's more acidic? The pKa of alcohol is 16, and you know that. The pKa of ammonia is 38. All right. Now, obviously, alcohol is more acidic, but just on a side note, how much more acidic that is? Well, pKa 16 is Ka of 10 to the negative 16th, right? pKa of 38 is the Ka is 10 to negative 38th. So 10 negative 16th over 10 negative 38th. That's 10 to the 22nd time. So 10 to the 6th million, so million, over trillion, whatever they call it, millions times stronger acid than ammonia. That's a lot stronger, right? So stronger acid is weaker conjugate base, right? Weaker acid, stronger conjugate base. So amide is stronger base than the ethoxide. Okay? All right, here's how we do it. Now, his explanation, right? I'm going to start with the strongest acid have a weak conjugate base. How come though? I'll show you some example here. Start with hydrochloric acid. We all know hydrochloric acid is strong acid, but its conjugate base chloride is super stable. It's a weak base. It doesn't do anything, right? Chloride is really stable. Think about this. Where do you see chloride? A lot in sodium chloride, salt that you eat, really stable, right? If you go to the ocean, that's the whole sodium chloride, a lot of chloride in it. Chloride is one of the most stable ions that we have, right? So strong acid, weak or stable conjugate base. See that? Give you another example. It's going to be opposite, right? I'm going to pick a weak acid here. So weak acid, for example, water. Water is super stable. Why do you see water? Everywhere, in the air, in the ocean, in your body, it's pretty much everywhere. There are weak acid, which means stable. Stable acid, weak acid is conjugate base. It's a bitch. Its hydroxide is really strong. Where do you see hydroxide ion? Do you see hydroxide ion on campus? Like walk around, hey, there's hydroxide ion. No. It's really reactive. Okay. Hydroxide have to be kept in a dry place, otherwise it would absorb water and become something else. It become water basically. All right. Really strong base. All right. Another example, ammonia. Okay, one of the weak acid, and its conjugate base gonna be the opposite. Right? It's a devil. This guy is a devil. Really strong. React violently, pretty much everything. So watch out right here. We're gonna use this guy in alkyne chapter. Alkyne is one of the most stable, but can also react with this guy. This guy is real strong. All right. So my point is, if the acid is strong, okay, right, this strong acid have a weak conjugate base, right? Weak acid have a strong conjugate base. So they have an opposite reactivity. Now, if I ask you, who's the strongest base on this page? Who's the strongest base on this page? Well, you have to look who's the weakest acid on this page, right? The weakest acid is an alkane, and its conjugate base is one of the strongest acid known, right? So it's strong. So it's strong to the point that, so we have the Grignard reagent that's going to learn it in alcohol chapter, right? So Grignard reagent cannot be used in an aqueous solution because it's so reactive that they can react even as a stable compound like water. If you want to use Grignard reagent, you have to do a reaction in something that really inert, like an ether, which is because all protons here are proton of alkane, and the pK of alkane is 50. Okay, it doesn't do reaction with the Grignard reagent. This guy is really strong base. All right. Okay. All right. Let's say this is a true story. So when I was in a PhD program, so I just I did synthesis. I'm an organic synthesis. One of the synthetic route that I have, one step from the million step, right, is protonation, or add a proton to ethanolamine. Okay, we call ethanolamine because it's an ethanol unit, right? 2 carbon, and with an OH alcohol, there's an ethanol unit. We have amine in it, we call ethanolamine. All right, so I have to protonate or add proton into ethanolamine, but the question is, I have 2 functional group here. Who's gonna take the proton from hydrochloric acid? Right? I have ethanolamine in solution, add a hydrochloric acid into the solution. My question I have to ask myself is, who's going to react with hydrochloric acid? Is it going to be alcohol? You get a hydronium ion looking thing like that, or amino group going to react with hydrochloric acid, make an ammonium salt, look like that. So what functional group is more basic? That's a question I have to ask myself. If it's more basic, it will attack proton, and you guys know that's how it works. Okay, the base is a species that is a proton acceptor, right there. So who's more basic, an alcohol and amine? Well, we have to look at their conjugate bases. Okay, I will draw out same thing. Draw out conjugate bases of these two. The conjugate base of an alcohol is this guy right here, right? And the conjugate acid of an amine group is this guy. Right. All right. So who is more acidic? Right. We know that this is the conjugate base of an alcohol, but it's not an alcohol anymore. This is hydronium ion, or pKa negative 1.7, not an alcohol, not 16. This guy is 16, but its conjugate base is hydronium ion. Look like that, about negative 1.7. And all right. Now compared to the conjugate acid of an amino group, so ammonium ion. What's the pK of this guy? Look back up to the pKa table. It's about 9. Now this is about 9. Who's more acidic? Of course, this hydronium ion is more acidic, right? More acidic, stronger acid, weak base, right? Weaker base. So who's a stronger base? The amino group. So the amino group gonna take on the proton of hydrochloric acid, and it's going to go this route. That's how we do it. Okay, so we can use the pKa value to determine the basicity of the conjugate bases. Okay, all right, go to the next video.